much. This is right.
Ben's got the jazz hands down there.
Then it's got the jazz hands. As I say, this guild is mostly about an introduction to Solidity, an introduction to smart contracts, but more than that, a kind of broad and sweeping look at how we actually interact with Ethereum, what MetaMask does, the ways in which we can think about safe and secure patterns when interacting with these new kinds of networks, as well as creating new things on them. The intention is not to make you into shadowy supercoders, but to give you the tools, knowledge, and skills you need to actually make informed and insightful decisions about what you choose to use, how you choose to use it, and what is happening when you click certain buttons, right? So often the dark patterns in user experience design and other things which have developed as a result of modern technologies incentivize us to just click like monkeys on a page without ever thinking about what's actually going on in any given situation. And the great opportunity of these open and permissionless networks is one of understanding, collaboration, peer-to-peer insights, right? We can really help one another rather than create new and more efficient systems for manipulating other people and making money off their attention. So that's kind of like my intention here. And as I say, please feel free to stop me at any time that you like, to ask any question that you like. Nothing is too simple or stupid. The whole point of this particular guild is that I am an extraordinarily simple and stupid person and would love it if I can share that simple stupidity with others. If you look in the kernel syllabus itself, you'll see that there is in module 3 piece on asking better questions. And this thing about asking questions, like if you have the courage and the vulnerability to ask something really simple, it's what's on everybody else's minds already. It's just that they don't want to ask it for you. And it really helps all of us get to the core of the questions that we actually have, and to have like honest and interesting learning environments created between us. So with that in mind, before we begin to lift the veil, are there any questions about the preparation or just the general structure of these particular sessions now that we've handled calendar and other administrative stuff? Wonderful. As I say, feel free to stop me at any stage because I'm not sure that I can speak for 2 hours straight, but we'll see.
I got a question.
Please.
Are we going to only learn Solidity, or are we going to learn any Viper?
In these 4 guilds, it will be focused only on Solidity because that's what the Ethernauts tutorials are written in. The channel itself will be open for comments, questions, and various investigations of Viper. I know the people who wrote Viper. One of them happens to be a South African. So if you have a particular interest in that and you feel because you're a little bit familiar with Python that Viper is the way for you, outside of these particular sessions in that channel, which is open all the time and in which you can ask anything to do with these sessions or just smart contracts in general and other languages, then drop your question in there. And if we can't answer it, then we will find the people who can.
Thank you.
For those of you who have no idea about any of the words that I just said, there are 2 major smart contract languages, the sorts of languages in which we write smart contracts on Ethereum. The one that we're going to deal with today and for the rest of this guild is something called Solidity, which is a very misleading name considering how many footguns and hacks and problems there have been with it over the years. But it is the most readable and accessible because it is most similar to a language called JavaScript. So if you come from like a web development background, or really like most people who begin learning how to code, you begin with HTML, which is hypertext markup language. What this web page right here is written in, this is HTML. It's styled with something called CSS, which is cascading style sheets. And that is what like makes the text appear a certain color, or you know, sort of structures the sidebar menu and then this main part of the page and the right hand menu. That's all CSS. And then in order to have like funky little interactions, these nice little things that happen, the arrow doing its thing and the menu expanding, you write something called JavaScript, which is, it's more programming. It says like, if this happens, then do this. Or for each of these kinds of things, do X, Y, and Z. So JavaScript is really like the beginning of programming for many people. And that's very similar to what Solidity is. If you can write and read JavaScript, Solidity is pretty accessible. Viper is, you know, like when Ethereum got going, there was Solidity and there was another language called Slither, which was more Python-like. You know, so like these are the two main routes into programming. You either come through a web background, HTML, CSS, and JavaScript, or you like did some math, statistics, some kind of data science thing. And because you come from that background, Python and R and these kinds of languages are a little bit more popular in that world. There are, you know, Python is it's a really fantastically powerful language. Lots of people really love it. And Slither was the kind of Ethereum version of Python. It was also full of security problems and was eventually abandoned. And now today we have Viper, which is a much more Python-like language for Ethereum. So these are the two languages that you'll hear spoken of the most. And yeah, if you're sort of more familiar with the web, Solidity is probably the most accessible and easy to learn about. If you're more like statistics, MATLAB, R, data science, that kind of stuff, or even like machine learning, then Viper will maybe be a little bit more accessible to you. There are better tools for Solidity though, and that's something that we'll discuss probably in the next session. So what we're going to be doing today is having a look at this Ethernaut tutorial, and I definitely don't want another tab. If you can open it in your browser, you should have the link from here, but I will also just drop it in the chat. Somebody else can. Right. And before we really like get into what this is and how we're going to be interacting with it, there are a few other things that I want to talk about, because one of the first step of our preparation here was to install MetaMask and create an Ethereum account, which is kind of like, it seems very obvious, right? You have this little fox in your browser and it's wonderful, and it kind of looks at you and watches everything that you do on web pages. But what actually is MetaMask and what is it doing? Because we're very quick to recommend these kinds of things to other people who want to get involved without really necessarily understanding how this stuff actually works. You know, how is it that MetaMask connects me to Ethereum? What role does it fulfill? And how can I explain that to other people in an accessible and non-technical fashion? So what MetaMask really is, although like most people will call it a wallet, another and perhaps more descriptive way of discussing it is it's a keychain, right? That you don't have a wallet in these kinds of networks. What you actually have are key pairs, right? And MetaMask is where you hang your keys for interacting with Ethereum. The easiest way of understanding what these key pairs are is by analogy to your home. So your public key, the address that you share with everybody, and you say, hey, send me some ETH, send it to 0xDE3468, whatever it is. That 0x string is your home address, So I can say to people, hey, I live at number 1 Grosvenor Road in South Africa. Come and visit me, It's no problem to share your home address with the world. It's public knowledge anyway. But I would never hand out my front door key to people. Right? I would never say, hey, come and visit. And so your private key is very similar to the front door key to your home. You would never hand it out. You tell people, hey, this is where I live, come and visit me, but I'm not going to give you my front door key. This is kind of how a private and public key pair works. And it's what MetaMask is actually doing. So when you install MetaMask and set up an account, what you're doing is creating one of these key pairs. Your private key, your front door key, is kept only on your computer, right, in your browser. It's never transported anywhere, and your public key is the address that you tell people about. And in order to use MetaMask to actually interact with Ethereum, what is going on is it uses something called RPC, right, which is a remote procedure call. So you navigate to a site like Ethernauts, which has the code required to interact, to form transactions, which can be submitted to Ethereum and read there. Those transactions are signed with your front door private key in MetaMask. And then that signed blob of data, whatever it is sent via a remote procedure call to MetaMask's servers. And they're the ones that submit it onto the Ethereum network. So MetaMask does run some servers, and there is this aspect of dependence on them when you're using MetaMask, but they never actually see your keys. All they ever get are these signed blobs of data, which they submit onto the chain. Then, your transaction gets submitted onto the chain. It's either successful or it fails. That information is sent back to your MetaMask instance, and we'll discuss a little bit how it injects that information into any web page that you're looking at. I know that this kind of sounds a little bit boring, perhaps a little bit technical, but it's worth understanding the protocols that we actually use. RPC is not the only one. So the most famous one, the one that you'll be most familiar with, is HTTP, right? HTTP is the hypertext transfer protocol, and it operates, our computers have these things called ports, and ports are really just like a specific process or a type of network service that your computer can connect to or provide. HTTP, for instance, operates on port 80 in your computer, right? HTTPS, which is what Ethernauts here is using, and you can see that because there's this little lock icon these days, is on port 443, right? SMTP is port 25. That's the simple mail transfer protocol. So when you're sending an email, you connect to port 25, and that's where you broadcast or receive data from. SSH, which is the secure shell hosting, secure shell hosting protocol, which is what we use to tunnel from my computer onto a server, for instance, is port 22. So each of these services, which defines its own logic, whether it's hypertext transfer or simple mail transfer or file transfer or secure shell hosting, they each define their own service, and that's how we actually communicate. All of these services are built on top of what we call TCP/IP, right? Let me get this right. Transmission Control Protocol / Internet Protocol, and it's worth kind of just recognizing how people are always kind of talking about DeFi Legos, right? It's really interesting because it's true, but it's also this is how the internet has always been built. You have TCP/IP, and then you have all of these Legos built on top of it that are kind of critical to our ability to communicate with one another. and which we take for granted. And in understanding how these things actually fit together, we can see that, like, okay, MetaMask is something that's interesting, and I can have a fairly high degree of certainty about trusting it, because I know that, like, how it actually works is generating these critical keys for signing transactions that are only ever in my browser and never get shared. And then I'm using a particular kind of protocol called these remote procedure calls to ask them to perform some service for me, in this case, submitting signed data onto Ethereum and then returning the results. So it's where, yeah, this is what the fox in your browser is actually doing. And the way that it does that is with a very clever but simple little injected provider. It's the last kind of technical introductory thing to discuss here, which is that this entire page that you see here, if you're familiar at all with web development, you will know that this is called the DOM, the document object model, right? This is where, like, the documents and various objects are rendered according to a particular kind of model that you've programmed. And MetaMask injects a little extra piece of JavaScript into that called your Web3 provider, which is something that we're going to use in order to interact with all of the various different tutorials that we go through here. And you can see that there are a lot of them. There's 23 these days, which is kind of incredible. There's a great deal of content that we can talk about, but we're not going to get through all of them, and certainly not today. We're only going to do 3 as an introduction to this. But all of this stuff, as I say, is just sort of the foundation for understanding that, like, Lego blocks, decentralization, keys, security, none of this stuff is new, right? What was fascinating, for instance, about the Bitcoin paper in 2009 was not that it presented some new technology, Diffie-Hellman key pairs and all of the sort of, like, lower level technical stuff that it relies on in order to function were not new. Most of that stuff had been around since the 80s. What is unique about Bitcoin is the way that it's put together and the kinds of insights that relies on, not just at a technical level, but also at the sociological one. There's a wonderful essay linked in the kernel syllabus called "Bitcoin is Worse is Better" by an incredible internet essayist called Gwern, which I can share in the Solidity channel after this guild. But Bitcoin is a terrible design if you're a pure cryptographer. Really, it makes almost no sense. It's so inefficient, that everybody gets all of the data all of the time is an incredibly ridiculous design if you're an actual computer scientist or cryptographer. But the point about these kinds of things is that it's generalists. It's people who are broadly aware, have unique and yet wide perspectives that can see ways to implement existing technologies in interesting ways. So forgive me for boring you a little bit about all of these different protocols that the internet is built on, but it's worth kind of understanding what the hell is going on when you're looking at a web page, because, like, we just sort of take it for granted. It's just like, oh yeah, let's browse to kernel.community and there it is. It's incredible the amounts of the giants on whose shoulders we stand just to render a single web page, let alone talk about remote procedure calls and signing data locally and submitting it to a service to broadcast it onto Ethereum for us. The other thing that I missed on this particular front, which I've sort of stumbled into by mistake, is that TCP/IP is interesting because there are actually 2 major protocols used for broadcasting data. TCP is, as I mentioned, the transmission control protocol, which is one of them, and the other is UDP, which is the user datagram protocol. Not super relevant to what we're talking about here, but it's worth understanding just for one reason only, which is that Bitcoin can function completely on UDP, whereas Ethereum requires TCP as well, which makes slightly different security guarantees for these 2 networks. The major difference between the 2 is that TCP requires a handshake. Basically, like, TCP is error-free, and it requires me to like go to the person that I want to send data to and like get their agreements that like, okay, we're going to open this channel between us and we're going to send stuff and receive stuff, do all of these wonderful things. And it's a little bit slower, but there's no errors in TCP. It's based on this handshake protocol, whereas UDP is just like, broadcast everything. And I don't agree with you that you're going to receive it first. And so there are certain errors that can come about as a result of that. And the reason that I tell you this is because when people start talking about things like censorship resistance, understanding that, like, for instance, Bitcoin transactions can be completely formed with only UDP is quite important from a censorship resistance perspective. Like when people say that you would have to shut down the internet to stop Bitcoin, it is very true. When people say that you would have to shut down the internet to stop Ethereum, it's slightly less true because of this reliance on TCP. So that's some of the protocols that are going on. How do we actually like look beyond what is going on our screen? Yeah, how do we? The title of this tutorial is "Lifting the Veil." So how do we do that? And it depends on what computer you're using, but I'm on like a Linux machine. I use Ubuntu as my OS because I'm South African and I love Ubuntu as a philosophy. But for me, it's Control-Shift-C, which opens up this lovely little pane on the right-hand side of my screen. For Mac users, it should be Command-Shift-C, and for Windows, also Control-Shift-C. Otherwise, there should be like a kind of preferences bar in which you can open your developer tools. While you're doing that, and feel free to yell if Control-Shift-C or Command-Shift-C do not work.
Yeah, for Windows people, it's Control-Shift-I.
Control-Shift-I. Thank you very much. Yes, I'm going to need lots of Windows assistance. I've lived a lot of my life with a deep bias against Windows, and it becomes a problem in these kind of tutorial sessions. But Control-Shift-I. Thank you so much. What is going on here before we get into the console, which is what we're actually going to need for Ethernauts, is that you can see I've got this little like select an element thing selected, and it is showing me the code, right, that is actually rendering what I'm seeing in my document object model on the page, right? And using this, I can go and select anything on the page. And this is like what it means to have an open standard, right? Because here in my styles section, if I select an element on this page, I can do what I wanted, right? So because I understand CSS, I can just say, remove that from the page, right? The web is not some fixed thing that we consume from. We can participate in it. We can do stuff. It requires knowing Control-Shift-C or Control-Shift-I and a little bit of CSS in this case. But you're really in control to a large extent. So of course, that's limited by what is being served to you, of course. But it's kind of cool, right? That with a very simple little bit of knowledge about some CSS and the ability to open your console to look at the code that's actually being rendered, you can all of a sudden have like a far greater degree of insight and control into what you see, how it's presented, all of this kind of stuff. The Elements tab in your console is what is dealing with the HTML, the hypertext markup language, and the CSS, which is the cascading style sheets, which is what I just kind of played around with to remove or display content. Like, I don't really like the OpenZeppelin team that much. I don't listen to what they have to say. So just take that away for now. It can be useful. Sometimes it depends, like some sites they actually have like good developers and you can't do this kind of thing. But there are certain sites, specifically if you have like a local news site or something that uses a paywall, sometimes you can get past it by just, adapting the HTML or the CSS. And off you go. You don't need to This is why Vitalik, in some of his posts, if you've been reading his blog because of his talk yesterday, you'll see that he says that like oftentimes having time lock voting in your contract is kind of like a paywall. It's highly ineffective and it's only really just annoying. The reason it's highly ineffective is you can mostly get past it if you know a little bit of code. The other important thing in your web developer toolset, the elements is HTML and CSS. The console is where we interact with any kind of JavaScript that the site is serving. And this is what we're going to be using for the duration of these tutorials. We'll be using only this console and one other thing in next week's tutorial and in some of the others, which is called an integrated development environment. It's called Remix, and it's provided by the Ethereum Foundation because we'll need to write some of our own smart contracts. But I think that it's enormously cool that without any extra tools, only our browser, we can learn a lot about smart contracts, and not only learn a lot, write our own and interact with a whole bunch of smart contracts that are deployed already. And through these very basic kind of transport procedures or remote procedure calls that MetaMask is going to help us with, we can do an extraordinary amount, which is really quite exciting. So if you're with me and you have your web console open, your MetaMask functioning, and in particular set to the Rinkeby network. So if you go to if you unlock your MetaMask, you go to this top little thing and you choose Rinkeby, that'll be good. And hopefully everybody tweeted after following the instructions on the Rinkeby faucet, and you have some Rinkeby ETH. If not, you can drop your address in the chat, and I will send you some. So I'll be watching that. If not, just yell and I'll. Okay, I see Amanath. Oh God. Okay, I'll do Amanath. If somebody can do Nazreen and Bella. This one time. Okay, Amanath. Thank you, Karen, for doing Nazreen. I will do Bella. Somebody's got Karina. Thank you, Nate.
Should I send some of what you have sent to me as well to other people?
No. That's okay. I've got Bella. Someone's got Karina. Someone got Nasreen. So we just need somebody to send to Michelle. Otherwise, I'll do that in a moment. Thank you, Michelle. That's been done. I'll do Denise if somebody can do Ernesto. Wonderful.
And really quick, how come if you do have Ethereum in your MetaMask, but on Rinkeby, then it doesn't show? How come it doesn't transfer? Because I have on the Ethereum mainnet, I have Ethereum in my account.
Thank you, Denise. Exactly, it happened to me.
But I freaked out for a second, you guys, because I was like about to go see, and they all said zero, and I was like, "Oh my god!"
It's a it's like a separate. It's like a separate network, so you have to go to a faucet and get separate ETH for that network. Yeah,
because
so they're like totally unrelated networks, but yet the same network.
It's the testing network, right?
Yeah.
Yes. Okay. Yes.
So there's Rinkeby specific faucets you can go and claim Ethereum to get into that wallet, but your mainnet assets don't reflect.
Interesting.
Because your mainnet's real money, right? Mainnet is real money that you use, and testnet is just like synthetic play money.
Got it.
Yeah. So Denise, Mark is right that they are completely separate networks, but what is they share exactly the same architecture, right? And the reason that we have all of these different test networks is because it's really important, like given the nature of blockchains, when I deploy code onto the Ethereum mainnet, it's there forever, right? And there's no taking it back. So like when I'm developing like a web page like this, it's so easy for me to just kind of, like have my machine developing locally, and I can like, try a whole bunch of code out and see if it works. And if it doesn't work, no problem. I just kind of like delete it and try again and like change this here and change this there, and off I go, right? And like that's how development has worked for the last kind of 20 years, right? But on a blockchain, it's not like that. Once I deploy my code, it's there. There's no taking it back. So it was really important to make all of these different test networks in order to make sure that developers had these environments which are like similar to the Ethereum main network, but where like you can make mistakes, you can try things, you can test things, and it's not with real ether. It's not with the thing that people.
So this is what
trade.
Developers are talking about when they say testnet.
Yes, it's exactly
Got
this.
it.
And
Got
there are numerous different kinds which you can see in the drop down here. The first one was called Ropsten, then Rinkeby came along, then it was Kovan and Gurley. And like Kovan and Gurley in particular, they have different consensus mechanisms, right? There was the other thing that was quite interesting to test with these different networks, is that Ethereum itself is proof of work, which is the same as Bitcoin. So it's like you have to perform all of these computations to get to what is the right nonce, right? So like in each block, there are like a number of different things that are included. The most important are the root hash, which contains like information about all of the transactions in that block. Is just like bundled up into one thing, right? And then like there's another which is like the hash of the previous block, which is how we link stuff together. And then the other really important one to know about is the nonce, which is this like random number.
Yep.
But what we specify is how many zeros it has to have, leading zeros, right? And when we talk about difficulty on these networks, it's about how many leading zeros are there in that nonce, because the more zeros, the harder the computation is to find like 17 zeros in a row. So like
Right.
Gurley
And that's the
and
proof of
Kovan,
work, right?
yes, that's proof of work. And then Gurley and Kovan and these
Got it.
other
Yeah.
networks are ways of like testing, can we have the same kind of environment but with different consensus mechanisms?
And do these
Kovan, I
networks
think, is-
keep coming out because they just get improved and they're better for developers to test on?
They are, and also like, so you see, one of the things that happened was the first network, Ropsten, it was so interesting. It's such an interesting, it's like a whole nother tutorial, to be honest. But like, so when Ethereum launched, we had Ropsten, and that was where we all used to test our, so you can go and like find the graveyard of many smart contracts I've written and stuff on Ropsten. But what happened was that Ropsten got attacked. Because the ETH on Ropsten is not actually worth anything, all of the economic safety models that go along with these kinds of networks just collapsed. And so like people just ended up spamming the shit out of the network, because it was, you had all of these faucets, so you could like get as much ETH as you wanted, and then you could just like submit spam transactions the whole time and clog up everything so that nobody could test. And it was like, it's not like a mission critical thing for Ethereum, but it was very annoying for developers, because some asshole out there was trolling all of us at making sure that we couldn't test anything, because they just stopped the networks because the economic safety guarantees are not operational because the ETH isn't worth anything.
Got it.
But the other thing, the other thing that I wanted, it's a fascinating question and like a really interesting piece of history. So thanks for bringing it up. The other thing which is confusing, I think, for many people, right, is that like, although I've switched networks, my account is still the same. So why is the ETH like not there, right? Which is kind of your original question. And it actually, like, it takes me very, very briefly into how we actually, what is the relationship between your public and your private key? What is the relationship between my like home address and my front door key? And I thought, I'm not going to go through the whole article. I can share this in the chat. But here is a really neat little GIF. This is what an elliptic key pair, an elliptic curve actually looks like, right? And what is happening when we generate your keys is we're using the maths that is being illustrated here, and I will explain it because this GIF just loops. But we're using the maths that is based on this kind of curve to generate your public key from some private key. And the way that we do it is constructed in a very, very specific way so that you can always get from your private key to your public key, but never from your public key to your private key. And because of the nature of the maths here, your private key will always give you the same public key. So even though I switch networks to like Rinkeby or Gurley or Rupston or whatever, because I've got the same private key, I always get the same address, although like that address is in a different world, you know, so your house on Ethereum doesn't appear on Ropsten because it's a separate universe, although the architecture is the same and the maths is the same. And you can see how it's sort of being generated here. As we say, there's some like generator point, which in this particular diagram is just the origin, it's 0, 0. And then because of like a really neat thing in cryptography called scalar addition, you can generate a whole bunch of different points, right? So I start my generator over here at the origin, and then using that, I find some points, I drop a perpendicular back to the x-axis. Because of scalar addition, this green point is just like my generator point doubled. And I keep on doing that procedure where I find another point and then go back to the nearest line. And I get to my public key over there, right? Finally, this red point here, but the maths is constructed in such a way that K, the private key that is in my MetaMask wallet, is never accessible to anybody else. And you can't calculate K when you just have the private points, I mean, the public key points here. I don't expect anybody like this. This is just for your like delights and edification to know how these keys actually relate. The maths is kind of interesting. We can talk about it kind of offline, but I thought it would just be interesting to see, hey, this is what an elliptic curve actually looks like. And like you do some stuff, magic happens. And then this is how I end up with my 0x, in my case, 5F33 public key, which is this point there, that red one. And it's associated with some private key, which nobody can calculate if the only information that they have is that 0x5F33. And that address will be the same on whatever network I use if it has the same architecture, which is what is happening here. I hesitate to ask, does anybody have questions about that? Because my cryptography is dangerous at best. Otherwise, we'll continue.
Andy, I actually have a quick question. Sorry.
Please, Michelle.
Oh, okay. Sorry. Oh, no, I was wondering, so it seems like the relationship between private to public is like determinant, if that's the right word. Is it difficult or is it probable rather for someone to reverse engineer public to private keys? I guess I could have a security.
It's impossible.
It's impossible. Okay.
Yeah, let me not. Nothing is impossible. Without consumer level quantum computing, it's not possible to go from your public key back to your private key, right? It's just given the way that the maths is set up, it's not possible. But perhaps quantum computers could find a way of doing it. So that's the one caveat. It's not a probabilistic thing. It's just the nature of elliptic curves and the particular kinds of operations that we're performing here and the order in which they're performed ensure that for any kind of classic computer or certainly any human being, in order to, because the only part, there's no algorithmic way to move back from your public to your private key. So the only possible thing to do is just to brute force it, right? To loop through infinite, possible private keys, and then like maybe one of them sticks. The only machines kind of capable of doing that are quantum machines. And with the
Oh.
advent of quantum computers, like a lot of cryptography breaks, not just elliptic curves, but like RSA, the stuff that makes HTTPS that breaks. And there are bigger problems than your Ethereum address if quantum computers become like fully operational tomorrow. But one of the big research questions for Ethereum, and indeed many other people, right, is quantum secure algorithms for key pair generation, but also for other things. And if it's a topic that interests you, there is a wonderful site called Research, like this, which I will drop in the chat. If I can get the chat to appear. It's a discourse forum. And if you look for quantum secure, you'll find a lot of stuff. It's fair warning, like it's very nerdy. What else can I say about it? But if
Quantum
it's a topic
disaster recovery.
yeah, it's
Talk about
truly
nerdy. I've never
amazing.
even heard that. Quantum disaster recovery.
It's a lot
That's
of fun.
amazing.
The site in general, like if you're in any way a geek, you'll enjoy it. There's some genuinely amazing stuff here, and like if you're ever asked like why you're more bullish about Ethereum than Tezos, like ETH research is a great reason for that. Not just the quality, depth, and volume of the research that is done there, but also the culture. A lot of how we think about kernel and the kinds of learning environments that we would like to create and see propagate as a result of the work that we do is taken from ETH research, which is very open, honest, robust, precise, all the sorts of things that you want. It's this kind of like community-led deep research. It's really fascinating. Okay, so I think it's time to begin. Sorry, another question, eh?
Oh, just thanks for sharing.
Oh, pleasure. That's what these are about. And finally we've made it to hello Ethernauts. Incredible. Welcome. We've talked about MetaMask. We've opened our browser's console. And now we can begin to actually code some stuff as some more people join us. You see, the console is not just a place where we can read some of the JavaScript functions that are happening. We can actually speak to whatever code is being served by, in this case, OpenZeppelin, and hopefully, get some responses back. And the way that works is we have to write some of our own JavaScript. And you can see here that they actually tell you what JavaScript you can write because they're providing some kind of code that we haven't yet been able to see. You can actually sort of write player, and it will return your address. You can see that this address is the same that's being displayed in my MetaMask. It's 0x5F33. And the site is able to read that and return it to me when I ask for my player. And you'll also see that if you follow their advice here and you say, I want to get the balance of my player address, then it doesn't exactly return it to us. It returns this weird promise thing. And this is how modern JavaScript often works. That's because information is, generally speaking, sent about in what we call an asynchronous way. Then JavaScript, quite a while, many years ago, adopted this logical construct called a promise. And it basically, when I say get balance of the player to the Ethernaut site, it's saying, will you, because it knows that I'm a millennial and I'm really into instant gratification, it tells me immediately, okay, I promise to get you back the information that you need. That's really what's going on here. And there is a way of sort of getting around it, which is that we can use the await keyword. So this is like boomer crypto. It's like, instead of being a millennial and just like, you're like, give me my balance now. It's like, okay, I'll await whatever the result of this same call, which is get balance. And in case you're wondering, like, you can see here what's going on. It has like this autocomplete thing. You can either press the right arrow on your keyboard or tab, and it should complete it for you so that you don't make stupid typing errors like I was just doing. And there, if we are instead just a little bit patient with JavaScript and the promises that it's going to send back to us, it tells me that my balance is 2.56 ETH, which is what I'm expecting, right? If I look at my MetaMask again, then I can see that, hey, yeah, there's 2.56. So more and more I can understand that all of the stuff that pops up when I'm looking at my screen is just like a fancy intuitive wrapper for, you know, what's already accessible in my console. But this is the great world of what we call UX, user experience, that we don't want people just to sort of have to come in and type their own stuff on our site. We want to make it elegant and easy and intuitive to use. But this is really what UX people do, and designers, is they take this data, which is available at the level of code, and they translate it into hopefully delightful and engaging visual experiences, because we are primarily visual beings this time. So anyway, we know that we can look at our address. We know that we can do simple things like get the balance associated with this address. We understand that we sometimes have to be a little bit patient with JavaScript while it goes and fetches information to return it to us. And we know that the people at OpenZeppelin are really wonderful, and that they provide us with a whole bunch of other top level things that we have immediate access to in our console. We have our player address, but we have the Ethernaut contract itself, the main thing deployed on Rinkeby, which is what we're going to use to deploy all of our own instances for each level. And those instances are the contracts that we're going to reflect on and try to break, which is something that I'll discuss in a moment. But if we listen to their advice here, we say that, okay, if we awaits the Ethernauts, thing, then we can see that's, we call it as a function. My computer is a little bit slow. Please forgive me. Let's just look here. So this Ethernaut contract is, I wonder how much detail I'm going to go into. The main Ethernaut contract, as I say, it's what's responsible for keeping track of which levels we've completed, for creating new instances. An instance of a smart contract is exactly what it sounds like. There's a template in each tutorial, and we're going to deploy our own instance of that template, and that's the one that we're going to kind of battle as we go through. And this top level Ethernaut contract is keeping track of it. And the only other thing that I kind of wanted to point your attention to in this Ethernaut object is the ABI. So, you know, people are often speaking these days about like platforms like Amazon and the fact that they own their API, which stands for Application Programmer Interface. And what that is like Amazon has all this internal business logic that's going on, and they want to be able to share that with the world. Amazon is a great example because like they figured out, hey, you know, like we have this huge volume of people that are wanting to sell stuff on our platform. There's no way they can open our API.
Hi, Andy.
You can
I don't know if it's only me, but I lost you there.
I lost Andy too.
Yeah. Me
Yeah.
too.
Your voice,
Same.
like, it's like you lost complete signal. Sorry to interrupt you. You were there very inspired.
Right when you were saying, yeah, just talking about API, Amazon API, before you kind of got into detail.
Yep.
Okay, give me 1 second.
And it's sad. That was like the climax of the explanation.
Okay.
No, it's still laggy.
Can't
It's
hear
like-
anything
it's like-
still, yeah.
So you guys come here often?
Once or twice, you know. I hear Vitalik likes to hang out here.
Yeah, that was.
What do you mean? What do you mean here? Like here to
Just-
It's a
it's-
joke.
In the-
It's a message.
Aren't we? We're in the metaverse, right? Isn't that where
yeah,
we're?
that's the here that I was referring to.
the Metaverse Cafe is mind blowing. That is so cool.
Yeah.
It's
Yeah, that's
exactly
The gather.town.
All right,
or
so- Yeah, the gather town. I feel like that's just a great way of us all communicating, getting to know each other. For the Vitalik Zoom, I mean, it was amazing and so much of it was profound. Am I alone that a lot of it was over my head, or I don't know? Is that just on me?
Yeah.
no,
Yeah,
no,
it's-
you're not alone.
not alone.
It's really
Oh.
When you spend enough time in this space, you'll pick up on it.
yeah.
Definitely.
You just gotta be. You gotta sit in the discomfort of not knowing what the fuck he's talking about, and then eventually it all connects.
I was
It's
loving
really
it. I was
funny that
loving
was
it. but-
very complex to understand, even though it was non-technical. So you know, it wasn't like
He
he was
went
talking
0 to 100 very quick. Yeah.
That's all he knows how to do. He can't.
Oh,
Is it-
so sorry.
Hey Andy, welcome back.
Hi.
Thank you. Thank you for entertaining people in my absence. As I
No
say,
worries.
I run a very, very consumer grade laptop with Ubuntu, partly because I really wanted to kind of prove that it was possible to interact with these kinds of things with very unspecialized hardware, but then trying to broadcast Zoom and do the Ethernauts and maintain Slack is a shame. My poor computer has been taking a little bit of strain, but well, I'll make up with her afterwards.
We need to start a DAO to get Andy a new computer.
Truly. Anyway, please excuse me. What I was saying was to do with this ABI, right? And that's
I'm sorry, I have a super quick question on instances. Are those a function of time and like when you're actually doing the smart contract, or what is the distinction?
the promises.
Instances.
Yes. Yeah. So like you'll see, I mean, it'll make much more sense when we actually get to like the first tutorial, which says like get new instance. So like here is like the templates for the smart contract that we'll be attacking, which I'll explain in a moment. And when we get a new instance, we deploy like literally an instance, a replica of this smart contract, and that's what we attack. The reason that it's structured like that is because like if there was just one smart contract, then only one person could attack it. So we have to like deploy our own, and then we can become, in this case, its owner. We can claim ownership of it, and then off we go.
Got it. So it's just a single iteration of the same
Yes.
thing.
Yeah, exactly. So what I was saying, please, other question?
Oh, yeah, I was just wondering, like, when the instance is running, is that all on that site? Is that all happening on the blockchain, or is that happening like off the blockchain in your browser?
Yes, this is all happening on Rinkeby. So what is it's on a network that we're connected to, and we're using the injected Web3 provider, in this case our MetaMask accounts, right, which we needed to connect to the site. So OpenZeppelin serves some code from their servers, which has a whole bunch of JavaScript that as its first thing before it executes kind of anything else. And if you ever build like a distributed application, you'll see this, where it asks for like window.ethereum, like it asks for some kind of connection to Ethereum. And MetaMask is what is providing that in this instance, right? It injects a little piece of JavaScript, and we call it an injected Web3 provider, which says like, hey, here is this person's address, here is the network they're connected to, here is some other random information which allows you to get their balance, for instance, and some other stuff, right? And OpenZeppelin's code that they're serving to us here has the capability of like, okay, cool, we've connected to MetaMask, now we can pull the information about their address, their balance, the network that they're connected to, and use that to go and find, okay, it's Rinkeby, let's like look for our contracts on the Rinkeby network. And in the case that we find them, we can return all of this information about those contracts. Does that make sense?
Yeah, that makes sense. Thanks.
Sure. It was an interesting, like, again, it's a really interesting question, because like one of the problems that we ran into with MetaMask in like the early days, again, was huge privacy concerns, because this thing of like an injected Web3 provider is really not good because every single web page that you visited, MetaMask would inject this Web3 provider. And so what people started doing was like setting up advertising and other kind of targeted marketing campaigns based on visits to their site that had injected this Web3 provider. So it didn't give away necessarily exactly who you were, but like it was very, very revealing, which is why these days it has this like connection logic where any site that expects this Web3 provider will ask you to connect to MetaMask, so that MetaMask doesn't automatically inject your Web3 provider into any site that you visit. But that's how it started. So, I'm sure that there is someone somewhere with all sorts of information about me, because I had MetaMask in the early days, and it sort of injected information about my account into the web pages that I was visiting. So it's a good question. It's again like one of these little like small but really, really important gotchas that's are kind of worth knowing about, because we fixed them, but it wasn't always like that. So these just demonstrates, as I said at the beginning, that like there's no such thing as a shadowy supercoder developer born that way. It's just that we make a lot of mistakes over and over again, and hopefully if we're humble and curious enough, we can learn from them. But yeah, it's a really good question. I was talking just a little bit about this contract and the ABI and using Amazon to illustrate what this is really about, right? Because like people get very excited about platforms opening up their access. And what's really going on with Amazon is that they have all of this internal business logic about how to process new sellers, new items, connect them with customers, processing payments, all of this kind of stuff. And they knew that they couldn't handle the kind of volume that they were seeing just on their own, right? And so in that case, what you do is you create an API, an application programming interface, and you say to the world, look, here are the functions that we will provide you access to. You can code against these functions and get our internal business logic to trigger automatically without like submitting a request to Amazon customer service. You can just interface directly with our programmatic business logic. And that's what APIs allow you to do. Very cool. But like, as you'll see later on in the kernel course, APIs themselves have their own limitations. And the biggest limitation and the easiest one to illustrate is advertising. That Amazon has this infinite shelf space available, but there are still only so many number one positions on those shelves. And so you cannot solve the problem of discoverability and advertising using a platform. You actually have to use a protocol. And you have to use a protocol in particular that aligns incentives. We'll speak more about this in module 5 of the kernel learn track. But these ABIs are one answer to that, because what this is an application binary interface, and it gives you direct access to all of the different functions that exist in this contract. And anyone, anywhere connected to Ethereum has access to these functions, right? This is what the ABI provides us, and we can go in and see what each of these things is and does. And so we can fetch information about who the owner of this contract is, what level it's registered with, whether an instance has been created for that level, whether ownership has been renounced, whether the level has been submitted, whether it's been transferred, all sorts of stuff exists within this ABI. And this is the means by which we actually interact with one another's contracts. So if, for instance, we wanted to find out who is the owner of this Ethernaut contract, then we can call the contract object itself, which is Ethernauts, and ask for the owner function, in which case it returns us this address. And we now know that this is the owner of the Ethernaut contracts. So for this particular level, we're going to, as they say, get a new instance and then interact with it and see if we can do the things that are required to complete the level. And if you click this blue button here, you'll see some cool little stuff pop up in your console, and you'll be asked to sign a transaction because we're deploying a contract onto Rinkeby. You can see that this is the Rinkeby test network. Can people see my MetaMask pop up? I just want to check that.
Yes.
Wonderful.
Yes, we can.
Wonderful.
Yeah.
Can you repeat that again? How you got there?
So this is, if you scroll down on the Hello Ethernaut level, you see this Get New Instance button. You simply click that, and it should pop up this transaction in your MetaMask, because we're actually going to be deploying a contract onto Rinkeby. And that means that we're changing the shared state of Rinkeby, which is why we have to submit it as a transaction and pay for it. It's another idea that we'll cover, I think, next week when we talk a little bit about money and value, what it means to have shared space, what it means to have free speech that is priced correctly. One of my favorite little gotchas in the kernel syllabus.
Andy, some of us are confused about ABI versus an API. So can you clarify why Solidity doesn't have an API, and why are we using an API?
I mean, it's, for the intents and purposes of this call, it's pretty much the same thing, right? It's simply that every single contract has an ABI, this application binary interface, which specifies not just the functions that exist on it, but also the like constants that are declared in it. For instance, owner, right? If you like went and looked at the Ethernaut contract itself, this owner that we're calling is probably just like an address public owner. is how it would be declared in the contract, and that will make more sense when we look at the next contract. And what we're actually doing there for SID, I wonder if you probably do know this, right? That like any public variable has automatically a get function associated with it, which is what we're actually calling there. So any contract in this ABI provides access and information about every single one of its functions and the variables in that contract, right? What makes that different from an API is that the API is controlled by some company, right? So like Amazon doesn't expose all of their business logic to the world. That would be insane. They just expose the things that people need in order to sell or buy products, right? And no more. And moreover, Amazon, it's highly unlikely given how technologically advanced they are and the disaster recovery that they must have in place. But like their API could conceivably fall over, because they're the ones who are providing it. In order for this ABI to become inaccessible, Rinkeby itself, or in the case of mainnet, Ethereum itself would have to be inaccessible. So these ABIs, the concept is the same. They provide programmatic access to all of the functions that are a part of that contract, but the medium in which they exist and the way in which we interact with them is different. Does that help?
Yeah, so
Yes, two more
ABI,
people.
everybody can see,
Yeah, go ahead.
right, in real time. It's fully open.
It is. Sid, do you want to?
Yeah, I'm asking, like two more people had that question. So Michelle and one more person had that question. Is it clear for them?
Yeah, that was super helpful. Thank you, Sid, for checking, and thank you, Andy, for rehashing again.
Please, yeah. So I really appreciate you surfacing questions from the chat because I can't do that. So keep doing it. Just interrupt me at will. It's wonderful. I'm already getting sick of my own voice. So the more you do it, the more I'll love you.
Hello, Andy, please, I have a question.
Yes, Glory.
Okay, talking from the mobile side of things, I realized that most of the contracts, after writing them on the web, trying to consume them on mobile is kind of challenging because basically there's no API. I've seen most of the time it's usually JSON RPC and probably trying to work with the ABI with another platform to be able to consume the API. I don't know how that issue or that problem can be solved. I kind of find it challenging. Maybe after writing a simple contract like this to consume it on a mobile app.
Mm-hmm. Yeah. Ethernaut is definitely not set up for mobile, and in general, this problem is a persistent one. A lot of the work that I did in the early days of Ethereum was for a company called Status, who launched not long after the launch of Ethereum, and our goal was to ensure that you could run meaningful light clients on resource restricted devices like mobile phones, because it shouldn't be the case that you require any kind of sort of upper middle class hardware or good networks, bandwidth and data in order to interact meaningfully with these networks. I think that we're still not at a stage where that's the case, clearly. One of the hopes is that with sort of sharded networks and less heavy kind of consensus algorithms, we can eventually achieve that kind of light client access. But you're right that like accessibility is still a problem for these kinds of things. There are other tutorials, other platforms which are perhaps more mobile friendly, like Ethernaut is set up specifically for people with computers, and that's just kind of how it is. So if I find like mobile specific ones, you know, you can probably play crypto zombies more effectively than Ethernauts from your mobile phone. But you're right. That's yeah. This is it's not good on mobile phones. But there's an opportunity, you know. That's it kind of reminds me while we're speaking about this. There's this wonderful story of the Dalai Lama speaking at some big business conference, and a journalist comes up to him after his speech, says, Dalai Lama, you know, don't you think it's a problem that more than 99% of the world's wealth is concentrated in 0.1% of the people's hands? Dalai Lama says, you know, I'm a Buddhist. We never see problems, we only see opportunities. So now you tell me that 99% of the world's wealth is focused in the hands of 0.1% of the population. It's wonderful. We only have to change 0.1% of the population. So I sometimes feel like that about these sorts of things, is that like, I very strongly feel, and have spent many years working on making this stuff more accessible on mobile. It's not trivial. It really isn't, because there are so many different problems, whether it's data and bandwidth or whether it's the actual resource constraint, like resource restrictions on the device. And the ability of like ARM chips to participate meaningfully in these networks is not really great at the moment, but hopefully that will change. Not really an answer to your question, Glory, but I really personally hope it will change. I just also know it's difficult. So what we're going to do here is try and get through this particular instance and see if we can find the information that we need to submit it and pass the level. So, you know, Ethernauts gives us the first clue here, which is that we need to get some information about the contract. So if we do that, then we get this really neat message back, which says you can find what you need in info1, open brackets, close brackets. So what this is saying is like, there's a function in this contract called info1, and we know it's a function because of those brackets that signifies a call to a function. And in your web console, if you just press the up key, it will load your previous command. And instead of calling the info function, you can call the info1 function and see if it has indeed what we need. Annoyingly, it doesn't quite seem to have exactly what we need, but it does say, try info2, but with hello as a parameter. This is interesting. You know, we're not just going to call the function itself without any kind of parameter or anything in the brackets. Now we need to try and call this new function info2, but this time we have to pass a parameter. We have to tell it, here is some information, because often like functions expect us to like give them some information, and they take that information and they do things with them. That's kind of what a function does. And it's told us, put in hello as a parameter. I've put it in quotation marks there because it's a string. You don't need to know too much about strings, but what you do need to realize while we're doing this is that we're programming, right? This is programming. This is not very shadowy supercoder at all. All we're doing is looking at this object called contracts and then particular functions associated with it. And some of these functions expect information in order for us to receive their response. And if we've called the second info2 function with hello as a parameter, it says the property info num holds the number of the next info method to call. That's interesting. So there is this property called info num. A property is much like owner up here that we've already called, and we've seen the owner's address for the Ethernaut contract itself. So we're going to try and call the property on this contract that's called info num. So if we load our last command again, and instead of calling info2, let's just call this property info num and see what comes back. And well, it's a little bit of a mess. It's this object O, and if we look in here, it's just some arrays and some other things that are going on, which I don't want to spend too much time on. What's really at a glance kind of most interesting about it is there's this words array which has stuff in it. That's where we probably should be looking. And if we look in the words array, there's this number 42, right? And it says the property info num holds the number of the next info method to call. So, if we think about this a little bit, it's probably got something to do with 42, but like, I'm not sure. I don't really know. I mean, like, there's this weird O thing with like arrays and, I don't really know what's going on here. So if I just, I don't really know what to call next. If I just like look at the contract itself, what actually is going on with this contract? And I can actually see, its ABI and all of the information associated with it. And if I look here, there's info, we've called it already, and info1 and info2. And then info num is the property that we've just interacted with, which gave us this strange thing back. And like, if we look here, aha, there is an info method 42. So it must be that 42 that was in here. And we can call it, and let's see what happens if we call it. And it says the method name is the name of the next method. So, clearly the Ethernaut team is kind of having some fun with us and just leading us by the nose through what it means to interact with a contract from our web console, to call these different functions, to look at the responses that they give, to consider how it is that these things are unfolding programmatically, right? Because what we're doing is coding. This is what developers do. They don't do it in their web console, but they write these functions in a text editor, and that's what makes up an application. So when you ask a developer, what are you doing? And they say programming, this is what they're doing. As I said, it happens in a slightly different environment, but it's not different to this. And we know that the method name is what we're looking for next. So if we await our contract, and you can see that it even has autocomplete here, and we're going to call the method name as the next method, and we get yet another message from the Ethernaut team, and this is the method name is method 7123949. Like, okay, I guess we better call that method too. And if we do that, then we can see that it auto completes. And we can call that function, expecting something in return. It says, if you know the password, submit it to authenticate. Well, that's really, I don't know what the password is. There's nothing in what we've looked at so far that has any indication of what the password could be. We've called info1, info2, info42, the method name. There's no password in any of this. So if I go back to my contract object, maybe there's some other information in the contract that could help me. I see the authenticate method there, which they're talking about. And there's a password method. Okay, so like, let me see, maybe I can call that password method and it might have something useful for me. That's kind of interesting. Let's see. It's like, aha, okay, this must be the password. Ethernaut 0. Okay. And so all I need to do is submit this password to the authenticate method, which is what the previous method told me. And I've now really sort of methoded out, but there's the authenticate method. And we know that it's going to require the string, which is Ethernaut 0. And if I do that, MetaMask transaction pops up. That's really interesting. So this must mean that the authenticate method is changing state on Rinkeby, right? So all of these other methods that we've just been interacting with are just, they're called view methods in the contract, right? All they do is they receive our request and they give us back some information. All of this information about the next method name is called method name, or info num holds the property of the next info method to call. All of that is just us reading information from the blockchain. But now all of a sudden this transaction has popped up, which means that we're not just reading information from the blockchain, we're actually going to write to it. We're going to change the state of this shared network. And if we're going to do that, we have to submit a transaction. So it's interesting, and we can talk more about this, especially if you have more questions about like what is the difference between like reading and writing. But all we've been doing so far is just reading information, finding the next method, and being walked through all of the different methods that this contract offers. Now we're actually going to authenticate. We're going to prove by changing the shared state with the correct password and our address that we cracked the instance of this contract. If I confirm that transaction, let's see, it's a little sent transaction waiting to pop up. I get a confirmed situation. I can look here. This is called a transaction object. It has the hash of this transaction. See if I grab this hash. This is always what people will send you as proof that they paid you. Oh, not Robston, excuse me. As proof that they paid you. So you can see that's the transaction hash returned in my console is, even if it's reloaded when I left. Thank you. So yeah, excuse me that it reloaded. As I say, my computer struggles a little bit, but that transaction hash that was returned in the blob is what you can find on Etherscan and what people send to one another to prove that their transactions have been made and that you have indeed paid someone or done some specific action. There are some other things in the transaction blob that you can look at on your own machine, seen as mine has handily deleted it, which the most important of which is probably the logs. One of the ways in which we bubble up information in a usable fashion for front-end engineers is through emitting events when certain things happen in mission-critical functions in our contracts, which we will look at, I think, a week or two from now. But the logs contain information that is not stored on the blockchain itself, but which can be used in your application to display different kinds of statuses and other interesting pieces of information to users. Logs are useful because, as I say, they're not actually stored in state. They're not part of the state of Ethereum, but they do help us figure out what actually happened, which is harder than it sounds sometimes. If you've managed to do all of that.
Quick question, Andy. Sorry to interrupt you.
No, please.
Yeah, well, I'm doing it because you said you wanted to get some people to help you rest a bit. So What you're doing now is just going through the different parts of the contract to read about it. And this is what you would normally do when I'm telling you like, hey, Andy, can you read this contract? So you would come here and start getting the inputting calls and retrieving information and back and forth, and kind of like trying an error and seeing how you can understand the logic of the contract. Or did something not go as usually planned and you had to like scramble around to try to find the way? Do you understand my question? My question is more like, did this not go how it's supposed to go and it's not as straightforward that I see you scrambling around? Or is this the normal way of, hey, here's a contract, good luck? Thank you.
Yes. So it's a wonderful question. This is going, apart from my computer crashing, it's going exactly as planned, because there are sort of two possibilities when we're interacting with contracts, right? The first, which is what's happening here, is that we don't have the source code, right? All we have is the address of the contract on chain, and we're trying to figure out what the hell does this thing do and what's in it, right? And that's why we like go and like look at the contracts and we're like, okay, what is in this thing? And like I can see some of the functions and different methods associated with it. And through interacting with these methods, I can kind of get a good sense of what this contract is and what it's doing, right? This is for like, yeah, when you're just given some address and nothing else, right? Like there's no other information in this tutorial about like what's actually in the contract. However, in other tutorials, like for instance, the next one, which we're going to get to very, very shortly, you actually have the source code for the contract, right? So here you can like go and read and you can be like, oh, this is exactly what this contract is doing. And that's what we're going to be dealing with for the rest of the Ethernauts tutorials, because they provide the source code for them and we're going to read the code and think about like what it's actually doing and how to hack it. But like in this first one, no information about what the contract is. And, you know, like if you look on Etherscan itself, you know, there are often, I wonder if I can like, find one for you. Let's look at the DAI contract, for instance, right? Now on Etherscan itself, you'll see that there's always this contract tab, right? And on this contract tab, there is sort of like two possibilities. In fact, let me just go to the actual contracts because looking at the token is not really what I want to do. You'll see that like some contracts on Ethereum have this like little green check mark, which is mean that the contract source code has been verified. And then like the source is actually displayed here and you can go and read, this is exactly what this contract does. In the case of DAI, it's not very useful because they use their own weird language, but that's like something else for another time. But like many contracts will not verify their source code. And so all that you will see is this, right? Which is the hexadecimal data that's actually deployed onto the chain. This is what a contract actually looks like to the Ethereum virtual machine. If people don't verify that this source code matches, that this hexadecimal data matches this source code, then Etherscan won't display what the contract actually does. And the best bet that you have for interacting with this contract is what we're doing now. So both possibilities exist, you know, like developers who are interested in providing services to the public, in proving that they're writing clear, secure, and sort of accountable code, always verify their source. I strongly recommend you doing the same, but some people don't. And if you're given a contract and you have to try and figure out what the hell is going on and nobody has verified the source of it, then you're sort of left doing what we've just done. Does that answer your question?
Indeed. Please, yeah, continue. Sorry, maybe this is getting a bit too into the weeds, but how do you verify and who says that something's verified?
So, yes. you'll see that there are a few things, right? That's when we go from high-level languages like Solidity or even JavaScript to what is actually executed by your computer, it goes through what's called a compiler, right? And the compiler, at the highest level, what it does is it takes like human readable and writable language, like function info1 with the logic, and it compiles it down to often binary code, zeros and ones, right? In the case of the Solidity compiler, it takes Solidity and it compiles it down to hexadecimal data, right? And it does so in a deterministic way. Hopefully. Some versions of the Solidity compiler have not done this, which have resulted in some fun and interesting bugs for people. And you will find, I'm sure, more than a few disgruntled developers who have suffered at the hands of this. But you can see that there is a compiler version that is specified here at a specific commit. There is whether optimization has been enabled, because that changes the hexadecimal data that has been output. And if you are able to, like sort of provide the reverse, basically, like when you're speaking to Etherscan or any other service that does this kind of verification, you can prove that this hexadecimal data comes from this code at this specific compiler version with the specific optimization flag set to whatever it is. So yeah, at a high level, that's, I think, enough information for you to explore more. Is that okay, Greg?
Yeah, that works. And I guess we're just trusting Etherscan to be honest in comparing those two.
Not necessarily, Etherscan, I don't want to get like too much into it, but like Etherscan provides an API actually that you can kind of hit with the contract address, the creation code, and your own source, plus these few little pieces of information, and you can prove deterministically, right? What deterministically means is, given the same inputs, I will always get the same output. Mm-hmm. So if I can like say to Etherscan, hey, look, this is what the output is, you have that. Everybody has access to everybody has access to this contract creation code, right? So I say to Etherscan, yes, this is what the output is. Here is the inputs and the flags, the compiler version and the optimization that leads to this output. And if I can do that, then I can prove that it's one and the same thing. And like, yeah, Etherscan is like a service that provides that, but you can do the same on any other block explorer that exists. It's not reliant on Etherscan, if that makes sense.
Yep. Thanks.
Did you pull this query from the Ethernaut OpenZeppelin page in terms of Etherscan? Or you just go to a random contract to show?
I just went to the DIA contract because I happen to know that it is verified.
Understood.
And
many contracts are verified.
Is it a red flag if a contract is not verified on Etherscan?
In my book, yes. Yeah. But like Mark's right. There conceivably some contexts in which like maybe not, but like it's a really, really, really great thing to check if you're unsure about like using some service.
Basically, Etherscan is just verifying that the output is coming from the input that the contract is written, right?
Yes.
And is there a reason why sometimes what's the reason why it's not verified? Is that because the person who created the contract is not sharing the input?
Yes.
Got it. Okay.
Sorry, while you're there, does it say who verified the contract?
I don't think so. Because like it's not verification is not like an on-chain action,
Yeah, my question is basically who verifies this? Like, How, because if I knew the mechanics, I'm not a developer and I could say, oh, I verified it. Like, how do we check and not just trust that it was verified by a reliable source?
Well,
if that's possible.
Sure. The point being that anybody can verify it. You know, anybody who has the correct inputs can verify the contract. You know, if you provide the correct inputs with the correct compiler version and optimization flag, then you have verified it. It doesn't have to be the developers of that contract. In practice, it almost always is, because they're the people who have written it. But you know, this is the point about like deterministic public stuff, is that like if you have the inputs, anybody can verify it, and like it doesn't matter who that person is. What matters is whether they have the correct inputs. That's all. Okay. So yeah, once you've done all of these things, you should be able to, and you've hit await contract.authenticate with the password, which is Ethernaut 0. You can submit your instance, which is one more transaction. What we're doing is we're saying to the main Ethernaut contract, here's this instance which we've conquered. Will you check that indeed we have passed this level? And if you submit your instance and wait patiently for this to be mined, which is another thing that I'll have lined up for our next tutorial, is maybe some elevator music. You should get these really beautiful, I really love the OpenZeppelin team. These guys are the best. Anyway, this rainbow effect through your console, it says, well done, you have completed this level. Thank you so much, Ethernauts. Make me feel so good about myself. We've made it. You can see that now that we've made it, they give us the source for this contract, which we've been blindly interacting with. So we can like read it if we wanted to, and you can see that like most of these methods are just pure methods, which means that they only can be read and return particular information. I'm going to go through the whole source there. It's a fairly straightforward contract, and I do know that we only have 10 minutes left, and I want to do at least one kind of read through and hack of a contract while we're still here. So I understand we're probably not going to get through this just in 10 minutes. I'm going to stick around afterwards, but please feel free to come and go as you need to. The recording will be available. So let's get a new instance of our fallback contract and get straight into it, which is going to be a lot of fun, because as you can see, this time we have the source available to us. And so while we're waiting for our transaction to be mined and for a new instance to be deployed that we can try and hack, we can take a look at what actually makes up a smart contract. And we'll try and do this line by line. The first line is a license identifier, right? In this case, it's MIT. It may seem like not that interesting, but it's worth just mentioning that like software licenses in open source are very important, and it's something that we care a lot about, because the kind of license that you open that you attach to any software that you put out into the world does matter. In this case, MIT is quite a basic license, and all it says, it's a share alike license. So it means that you can use the software for free. It's freely available. You can do whatever you want with it. You can adapt it. But if you do, and you publish your own version, you have to share it in the same way that it has been shared with you. There are quite a few different kinds of licenses like this. MIT, AGPL, and GPL, the sort of general purpose licenses, are most commonly used. The other popular one for people like myself is CC Xero, which is the Creative Commons Xero license developed by Aaron Swartz and Lawrence Lessig. Another piece of internet history, which we will discuss another time. But Aaron in particular was a genuinely incredible person who is deeply missed.
RIP.
Yeah. So that's the license. Open source share alike licenses are the ones that we like the most, and that you will see most commonly used across the Ethereum ecosystem, because that's what enables collaboration and cooperation from a legal perspective. Interestingly, for instance, the Uniswap v3 contracts are licensed under, I think, BSL, the business services license, which means that people cannot simply clone, copy, and use them as they like, because they give their own reasons in their blog post. You can read about it. It's not universally used, these MIT and GPL licenses, and there are conceivably contexts in which you would want to use a different one, but the most popular are MIT and GPL. The next line, this pragma solidity, this is where we're declaring which compiler version we're going to use. So big thanks to Greg for asking that question, because you specify before you write any contract the version of the compiler that you're going to use to get that contract down into hexadecimal data so that you can put it onto Ethereum. And again, you know, if you come to the NFTZ build guilds and some of the others, we'll discuss, you know, what this caret actually means and the implications that it has on security and these kinds of things, because all of this matters. But basically what we're looking at here is just saying we're using the 0.6.0 version of the Solidity compiler. And we're importing a library from OpenZeppelin themselves, because this is what OpenZeppelin actually does. You know, apart from make beautiful tutorials like this and do very incredible audits, their main contribution to Ethereum has been writing the majority of the libraries that all of us use for ERC20 tokens, for ERC721 tokens, fungible and non-fungible, the ERC 11, 15, 55 tokens. OpenZeppelin has so many different libraries, it's incredible. And again, we can't help but love all of the incredible people that work there, mostly in South America. They're really great. So if they ever watch this, you guys are the best, and girls, because they have some incredible women as well. Safe Math is one of the libraries that they had to write because of the problems with Solidity and how it handles addition, subtraction, multiplication, and division. And so this just makes sure that we are using a library which provides us with mathematical functions that actually work as we expect them. After Solidity 0.8.0, it's not been required, but since we're still back at 0.6 here, Safe Math is a good library to be aware of, because you can't just assume that maths in Solidity is going to work, which we will look at when we get to the token tutorial, which is going to have to be next time. But very basically, when you write a contract, you first have to declare, okay, I'm now ready, I'm going to write my first contract, and you give it a name. In this case, it's going to be Fallback, because that's the nature of this tutorial. I'm going to be looking at fallback functions. And then we're going to, you know, write a whole bunch of functions associated with this contract. You can see them down there. Before we get to the functions, we have to declare some global variables, right? So we're going to make sure that we use the Safe Math library that we've imported for any uint256. What this stands for is an unsigned integer of at most 256 bits, which is the most that we can have. You can declare unsigned integers of different sizes, and that will become again important in the token tutorial when we get there. For now, just this is a number, right? And it's a potentially very big number. So we're going to use Safe Math for any number that appears in our contract, is what we're saying. We're also going to have an owner of our contracts, which is an address. So Solidity is slightly different from JavaScript, because we declare what type of things our variables are. So this owner has a type of address. It's some address on Ethereum that has to be the owner of this contract. And there are some other sort of attributes that we can associate with this type. The one is that it's payable, so it can receive and send money. and it's public. So that just ensures that everybody can read its value immediately. For those developers who are here, like Sid, that means that you have a get function automatically written for you at compile time. The other thing that we have is this mapping. And mapping is another type, much like an address. You have uints, you have mappings, you have bytes, you have strings, you have addresses. You have some others which we're not going to touch on. And this mapping takes some key, in this case it's an address, and it maps it to a value, in this case a number. So there's this mappings object, which we call contributions, and what it is it's some address and some number, which is its contribution to this contract. That's kind of what we're talking about. The constructor is the function that is called once when we deploy the contract. So if you want things to be initialized as you deploy your contracts, you write a constructor function and you do what needs to be done there. So we've created this global variable called owner, and we set the owner to whoever sends the message that deploys the contract, right? And the other thing that we do is we initialize this contributions mapping, and we look at the address of whoever sent the message that deployed this contract, and we put its contribution to 1,000 ether. So before we kind of continue into that contract, let's just look at what we have to do in order to beat this level. We have to claim ownership, and we have to reduce its balance to 0. And in order, like if we just look through the contract here, we can see that any kind of withdrawal that we're going to have to make can only be made by the owner, who's set up in this constructor. And we know that in order to become the owner, you can see here, we're setting the owner to this message sender. We have to contribute more than what is currently set as the contribution for the owner, which is 1,000 ether. We set the first contribution of the owner to 1,000 ether. And if we look at this contribute function line by line, what it's saying is that anybody who calls contributes, it is a requirement for this function to run that the value of any message you send it is less than 0.001 ether. And we know that the owner's contribution is 1,000 ether. So, oh my God. Right? If the contributions of the message sender are greater than the contributions of the owner, then we set the owner to the new message sender, which means we can only send 0.001 ether per message, and we have to set our contribution to more than 1,000 ether. This is terrible. We're gonna have to sit here for hours. You thought you were here for 2 hours. You're going to be here for 20 hours if we just use this contribute function to try and claim ownership of this contract. There has to be some other way, right? There has to be some other way to claim ownership and withdraw all of the funds from this contract. Surely, surely. So if I look through the rest of the contracts, each of these, you can see that we've got our constructor, which is called once when the contract is deployed. This modifier, which is used to modify functions. So it's literally what the name suggests. And it says that, okay, we're going to require that the message sender is the owner. Otherwise, we're going to revert, which is what that little piece of code says, that underscore. It's just revert the whole function. So that's not going to help us much. We've got this function contribute, which seems awful, and it's going to require years of calling it with 0.001 ETH, which is not good. Get contributions is just returning how much we've contributed already, not going to help us. Withdraw, we have to be the owner to call it, so no good there. Then there's this, it's called receive. It's such an interesting thing, right? Because it's not declared as a function. And so what this actually is something called a fallback function, right? And that's why the name of this tutorial is fallback, because smart contracts on Ethereum have this feature where you can have one fallback function, which is what gets called if somebody sends a transaction to your contract that calls a function that doesn't exist on the contract. So you remember that, like, if we like get the information about our contract, and we can see like the different methods that exist on it, right? Like contributes, contributions, get contribution, the owner, the withdraw function, all this stuff. If I called like contract.andy and sent some kind of transaction using Andy as a method name, then it will like look on the ABI. So there's no method called Andy, and so it calls the fallback. That's one of the features of how contracts work on Ethereum. And when you don't, declare it as a function or anything, this is what the fallback function can look like. And what's going on here is considered very, very bad practice, right? To put any kind of logic in your fallback function is very, very dangerous because people can trigger it unintentionally, right? And you can see that there's something really interesting here, that we are changing the owner of the contract in the fallback function, right? So that's kind of interesting. This is definitely where we should be looking if we want to try and figure out how to become the owner so that we can withdraw the funds from the contract and beat the level, right? And if we look at the logic in this receive fallback function, it's the first thing I'll say is for like other developers on the call, like often fallback functions are just called function with the brackets immediately after them. The Ethernauts team here is trying to be clever by like calling it receive so that you are not immediately aware that it is actually the fallback function, but it is. Just because it has a name, it's not declared as a function, and this is indeed what will be called on any fallback. And we look at it and it says, okay, we're going to require that any message sent to this function is more than 0, the value of it, and that the uint associated with the address of the message sender in the contributions mapping is also greater than 0. And if both of those conditions are true, then we set the owner to the message sender. So that means that we need to do 2 things in order to gain ownership of this contract. The first is that we actually have to send a contribution so that the uint associated with our address in this contributions mapping is greater than 0, and that check passes. And when we call this fallback function, we have to make sure that we call it with a message value greater than 0. So if you remember from our previous example, we call methods on the contracts by dot their name, and the first thing that we have to do is call the contribute method, right? You can see that contribute has no parameters, not like that hello that we passed to info1, but it does require this message value, right? Is less than 0.01001 ether. I know that I'm moving a little bit fast through this, but we're also like running out of time, and I will sort of rediscuss this again, both in the course of the week and at our next guild session, which will not be the same time next Friday, but a time that doesn't clash. The main point that I want to make is that these globally available things, message.sender, message.value, there's also tx.origin, which is where the origin of the transaction, message.gas, all of these things are sort of readily available on any transaction that you submit to Ethereum. And the way that you do it is by, we could call the contribute method like that, just with no parameters in the brackets. But if we want to pass some value to it, then we need to pass in an object, which we declare with these curly brackets. And this object needs to have some value associated with it. The other slightly confusing thing about this value is that everything is encoded in way on Ethereum, not in Ether. And so it's all times 10 to the 18. So in order to have something less than 0.001 Ether, we're going to need a value which is 1 followed by 14 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which is 0.0001 Ether. For those of you who want to do the maths. But that should pop up a little transaction because I'm sending value, I'm changing the state of the network. And anytime Ether moves from my account to another account, there's some value, there's some change in the state of Ethereum. And we're also changing the state of this contract, right? Because we're updating the contributions mapping and adding whatever value we send, which in this case was 0.0001 Ether, to the key associated with our address. That transaction has been successful, and I can tell because the transaction blob has come back there. So I know that this particular part of the check is going to pass. The other thing that I need to do is make sure that the message value that I send whenever I call the fallback function is greater than 0. And calling a fallback function is perhaps a little bit unintuitive, but all you need to do is send a transaction to the contract. That's all you need to do to trigger the fallback. And that's why putting logic in these fallback functions is really bad practice, which is like the first thing that the Zeppelin team wanted to illustrate, because sometimes people used to do this and there were some nasty hacks as a result of this, this particular practice that crept in the early days of Ethereum. And so in order to send a, as I say, in order to send a transaction, all I need to do is like look at the contract and there should be a send transaction method on it. So it's just gonna end up calling the fallback function because there's no specific send transaction function coded in here, right? So it's going to default to the receive and it's going to fire this logic. So I need to make sure, much like I did in the last transaction that I submitted, that I also attach some value to this. I just need to make sure that it's bigger than 0. So this time I'm only going to put 12 zeros there. It would be 0.00001 ETH. 12. If I just send a transaction without saying what function I'm calling, it's immediately going to call this fallback function. And because I've made sure that my contributions for the address that I control are greater than 0, and the message value that I just passed when I sent this transaction was greater than 0, hopefully I should become the owner. Hopefully, we'll see. There's great suspense as it processes my transaction. It looks like it was successful. I have a transaction hash, there's a receipt. You can see the logs that I spoke about. There's no logs because no events are in this contract, but you know, it's got a status of true. So I'm pretty hopeful that I've been able to read and hack this contract correctly, and I can check if I just call, you know, before submitting it or anything, you know, finding out that I was wrong. Maybe I can just see who the owner of the contract is, right? And hey, it's my address. So this logic has indeed been executed on Rinkeby. I've become the owner of this address. And if I submit the instance, then hopefully I'll get the same rainbow congratulations from the Ethereum team. I mean, from the Ethernaut team in my console. So while we wait for that, I'm sure that there were a lot of questions because I went through that really quickly, and I can promise that we will get to reading these contracts and become familiar with them and become
You need to withdraw.
Yes, I got the same thing. It says you
Oh,
haven't
sorry.
cracked
You
the
know what I
level.
didn't do? I'm such an idiot. Thank you very much. I need to. The other thing that I need to do is withdraw. I need to reduce its balance.
I'll
to
withdraw the
0.
balance.
I'm so sorry about that. I got a little bit ahead of myself, but I told you we were going to make lots of mistakes. So contract, if I call the withdraw method, I see that I don't need to pass any parameters to it. I just call it and it transfers the entire balance of this contract, the entire balance associated with this address, which is this contract, to the owner. So if I do that, then that should be good. So as I say, this is really about, making mistakes, seeing big red stack traces. This is something else that good developers are intimately familiar with and have spent hours looking at deep into the night on cold winter evenings, considering what it is that they have to do to make their computer do what they want. But now that I've withdrawn the balance, I should be able to submit the instance and claim that I've completed this level. So yes, as I was saying, like, I know that this would have seemed very, very kind of quick. And when we go through other contracts in the next 3 guild sessions, we'll have much more time to, there's my rainbow. Thank you so much, OpenZeppelin. We'll have much more time to actually like look at the source code of the contracts, to consider them carefully, to think about like what each line of code is doing, and to become more familiar with the way that Solidity works and all of the little things that are happening in these smart contracts. The major intention for this session was to understand a little bit more about MetaMask, about how it's interacting with Ethereum, about all of the different networks that exist, about some of the history, about the way the keys work, and how we connect web pages to contracts and how we can interact with contracts in various different ways. So do we have questions, other comments, general kind of, oh my God, dude, why the last 15 minutes feel like I know nothing? I'm very happy to answer all of these.
I guess my only question is, knowing, like, when we're going through that, you sort of already knew the contract calls to make. I mean, is it, say we didn't have someone guiding us through it, is this more or less just like experiment, like look at the contract functions, go through and just think, okay, what function would I call and how would I do it, and just kind of like guess until you're able to like figure it out?
Yes, very
Okay.
much so. As I say, there's also like, there are great written tutorials which will provide you with like exactly what you need to pass each level. So you can like use those as a learning aid, but it's really worthwhile, to sort of like read the contract yourself and be like, what is this thing actually doing? And how can I interact with it in like the way that I need to complete this level, to complete the task that is set for me? Because like, it's very, very easy to put in a few lines of code to your web console and be like, yes, I understand this contract. And it's not often the case. There are these subtle kinds of things which make this kind of development a little bit more involved, right? And like kind of sitting there and struggling, it's a wonderful way to really learn, because like it's later on in the kernel modules, one of the things that we talk about is learning how to learn. Like, how do you become passionate about the process of learning itself, not the content that you're actually, acquiring knowledge about at any given moment. And like a big part of that is becoming intimate with the struggle of not knowing, with discomfort, with unfamiliarity. And if you're like capable of like getting energy from unfamiliarity and from environments which are not what you're used to, and from things which are frustrating because they don't behave in the way that you expect, then you inevitably become a much better developer, that's for sure. And also probably a better human being. And I don't know, I'm not 100% certain about the better human being part, but certainly this thing of being like the ability to be in frustration, uncertainty, doubts, difficulty, unfamiliarity, and use it as a source of energy rather than confusion and anxiety is an incredibly powerful personality feature of some of the best developers that I know. And it comes from hitting your head against red stack traces endlessly. You know, and that's kind of maybe what like developers have to share with the world in terms of like their approach to things, because none of us were, apart from like a few people, you know, who are like virtuosos, like born to do it. I've watched Vitalik code and it's like that. You know, you watch somebody play a piano from 5 years old and it's just, this is what this person was meant to do. But for the rest of us fools, you know, we we just bash our heads against the red stack traces and our own idiocy and inability to understand. And the best developers are the people who are capable of just being in that and not giving up. So like, it's totally possible to go and find the answers, and I recommend that you do. That's wonderful. But as far as you'll learn the most if you like read the contract and be like, what the hell is this line even doing? And then think about it a bit. Yeah.
Hello, Andy.
Yeah, go ahead. Go ahead. I was going to ask your question.
Okay. So, you know, some of these terms are still a little bit confusing for me, even though I know the meaning literally speaking. So I know that DApp is a decentralized application, but I'm still not very sure when to say that this particular application I've built or this particular web solution I've built is a DApp. So at what point can I say that this is a DApp?
Always with the brilliant questions, Glory. It's a wonderful question. And it's not exactly straightforward to answer. You know, at the level of what we've been looking at now, you can deploy a contract with particular logic, whatever it is, and you can say that that is decentralized, right? Because it's not dependent on you in order to run. You know, like once it's on Ethereum, your actual like business logic in contract form, you know, all of Ethereum needs to go down in order for that contract to stop functioning. So in that sense, the mission critical logic of whatever you're doing is decentralized the moment you put it on Ethereum. But of course, it's not the whole story, right? Because we actually have to make the application that people interact with. And for the most part, many of these applications are hosted on private servers and served, you know, off, say, like an AWS machine or DigitalOcean or some other kind of provider, right, that is responsible for hosting your front end. And that makes it less decentralized, because if somebody hits that machine with a DDoS attack or whatever, then all of a sudden your ability to interact with your business logic is gone. There are different approaches to this based on different kinds of trade-offs that people make in different contexts, right? For instance, the Uniswap approach has been to open source their front end completely. And that means that anybody can run at the Uniswap front end, even if their particular instance goes down. It's very easy to spin up your own instance, and that provides some kind of decentralized guarantees, right? That's not completely frictionless, but it does mean that like people still have the ability, if everything on app.uniswap.org goes down, something, you know, a clone will very quickly come up. And Uniswap actually already has, you know, quite a few clones. And the next level up is to use some kind of permanent file storage network, something like IPFS or Arweave, which I'm a big fan of.
Yeah, I saw the Arweave extension in your browser.
Yes.
And
yeah, really
I met
like
with
Arweave.
I met with Sam in New York just this past week.
He's incredible, right? So yeah, we had a fireside with him in the last block. What an amazing guy.
So question, Andy, you know, when it comes to, let's say, you know, present day in terms of what's available, what is a fully decentralized stack that you believe today works in terms of having a full application experience that is decentralized and operates in a decentralized hosted way? Does that exist yet, or is it still not quite capable?
I think that Uniswap is probably one of the closest that I know of, because they do actually have like a fully functional front end on IPFS, which is not difficult. I mean, it's not easy to get right. It's easy enough to host a static website there. Very challenging to host like dynamic content. Like honestly though, for me, Mark, I must admit that like open sourcing your front end with a permissive share alike license and making sure that there are very clear instructions about how to run it is kind of enough for me. I'm not a purist,
Well, I'm thinking about this from the perspective that your website can't get taken down, right?
Yeah, then
we're
I think that's
like I can't, you know what I mean? Like basically writing a truly unstoppable application.
Yeah, I think that your best bets stack-wise would be contracts on Ethereum, any kind of front end using IPNS and IPFS. So just IPNS, which is the interplanetary name system, and IPFS, the file system. IPNS is what allows you to do dynamic content.
Is IPNS similar to what they're doing with IPLD, or is that different?
Yes, it's all part of the same crew. It's all protocol labs, right?
Okay.
And they're probably like the furthest along. I'm very bullish about Aweave as well. I think that's at the protocol level, they're more interesting than IPFS because they have this adaptive incentive game going on, which I think is totally fascinating and probably necessary for these kinds of storage endeavors over time. But your best bet from like somewhat mature developer tools at the moment, although I'm sure Angela would also have something to say about IPNS because she's explored it for us. But the most mature and kind of well-documented tools at the moment, contracts on Ethereum, front end on IPFS using IPNS as a routing service to handle dynamic content. Rich, I see that your hand is raised.
Okay, never mind.
Hi, thanks. Sorry, I showed up maybe 20 minutes late, which, I lost some of the earliest logic. So, but I think I clung on enough just to follow along. I like to actually look at code and see if I can figure out what it's trying to do. What is the logic? What is, but my question is about, I'm trying to understand if I'm in the right place. Because it seems to me like if we're not going to be doing any, hardcore coding, because that seems dangerous to me to like do anything that I shouldn't be doing. So I guess what I'm asking is this the right place to be if I really just want to be able to have conversations with developers, with, programmers, so that I know what I'm asking them to do, and so that just to make conversations more productive? Is this the right place to be for that?
Yes, it is. There's a few things. Everything is allowed. Don't be worried about not doing anything wrong. That's very much not a part of like the culture. It's that we iterate and make mistakes. This is why today we've been working on a test network and will continue to do that for the rest of this guild. So it's no problem. You will begin to like play around with some code here. So it'll make you really familiar and it will give you the insight that you require in order to speak meaningfully with like professional developers. So for all of those reasons, that's definitely like the right place. The other thing that I would say is that like in the other guild that I will host, which is the NFTZ guild, because I like names, we will actually like do more coding, and you're more than welcome to join there. Like these sessions, you can participate to the extent of your own desire and capacity. Like even in those sessions where we will be doing like much more coding than we have here. You don't have to like completely code along. You know, you can sit in and just watch and get an understanding for what's happening. There's no expectation, and there's no examination. There's no assessment. We're not going to kick you if you don't, I don't know, pass. None of that exists.
Great, thanks.
Welcome. Yeah.
Thank you.
Andy,
Okay.
I guess final question, when it comes to like something like a cache, in terms of like an AWS, I mean, do you think is IPFS basically can do what AWS does, essentially, is what you're saying? Or is like in a cache a sort of derivative of what a more synonymous AWS is?
Yeah, you know, this is the thing, is that when you try and host production things on like a fully decentralized stack at the moment, like IPFS, the reason that I'm like hesitant about it is not because it's not capable of doing it. It is. It's just painfully slow and like difficult, right? So it's no problem for a developer because like, cool, I can do the difficult thing if I really want to like have a totally unstoppable application. Like I just expect that that's going to be difficult to do because that's the nature of the trade-off that I'm making. But then when it's like hundreds of hours of dev work and I produce something which is so slow that like most millennials like Andy, who's just all about instant gratification, you know, like look at it for 5 seconds and like, oh, fuck this. You know, like that, it's that kind of problem that you run into. It's like UX based more than anything. So like, you know, like a lot of people have gone down that route and then they do end up saying, okay, like, but maybe I can cache some content in a more centralized place for UX. And if you're going to do that, then, yeah, I mean, like,
so having just like a cat, we still don't have a really good decentralized caching network that queries data effectively quickly.
Well, yes, you know, when Ethereum was launched, you know, I love these kind of sessions because I get to speak truth. When Ethereum was launched, there were two things that went along with it, right? Swarm and Whisper. Swarm was the file storage system, and Whisper was the
I
communication
remember.
protocol. Whisper is abandoned. I know because I worked on it. And Swarm is crawling along, you know. So we basically have a world computer where we only use CPU, but shh, don't tell anyone. It's funny stuff. So yes, we don't have a very good fast caching solution at the moment.
Yeah.
And, I think
that's something that we were working on. Yeah, that's something that we were working on before. When so I understand the need. I just wasn't sure if since something else has kind of popped up that has maybe done that, but I guess not. Which sucks.
When you say cache, you mean like temporary? Is that what that's referring to? Or?
Yeah, like basically readily like data that is, so you know, imagine because a lot of different applications, you know, decentralized applications utilize a lot of the same data. So you would have this idea of a caching network that has that data highly available, readily available in like, let's say, immutable chunks of data that are, you know, in our case, like at least what we were building, it was like we called them data blocks. So this idea of like immutable chunks of data that exist on a network that could be in many different nodes, some chunks of data more readily available than other chunks of data that could be pulled into an application very quickly, depending on like, you know, how often it's used by applications, because a lot of applications use a lot of the same kinds of data. And the more readily available you can make that and faster to access, the better for applications that are otherwise decentralized. So
but isn't that what the opposite of what the IPFS is for? So why would you want to use it?
Yeah, that's for well, you would need it as a complement, but it could all, I mean, depending on how you build it, like it could also be that very network. I think IPFS is maybe trying to do something like that, but the idea being is just like, it just makes the access to the data faster. So it's not as slow. That would be a complement to an IPFS or a similar, you know, content storage system.
Yeah, so like IPFS has deduplication, like so it chunks the data into smaller pieces. And if you have repeated chunks across different applications, it won't duplicate them. So it would try to reuse as many of those chunks as possible and saves on a lot of space that way. So IPFS itself works like a cache. And for your question about the backend, I think as of this year, there are these emerging technologies, like you can look up Akash.network. So Gitcoin is trying to use that for decentralizing quadratic lands and all those sites for decentralizing the backend. So we are slowly getting there.
Okay, happy people. Thank you very much for sticking it out until the end. I really appreciate it. Apologies for the slight computer interruptions. Mark, thank you for the many questions and providing, I think, entertainment while I was away, which is really the most important. If I drop again, I'm gonna.
We were pretty quiet while you were away.
Okay. Please, be the Shubhap girl dancing in the background if it happens again. Whatever goes. Sid will join you. He's got all of these wonderful animations. I think that he can perhaps provide as well. Otherwise, I'll try and go maybe think about a new machine. But yes, I really appreciate all of your time. Thank you so much. This guild will happen again next week at a slightly different time.
Thank you,
Thank you,
Andy.
Andy.
Thanks, everybody.
Thank you. Bye-bye.
One more question,
Andy.
please.
Bye-bye.
One more question.
Thank you, guys.
Sorry,
One more
Andy.
question, please.
sorry, I'm
Okay,
here.
so when we are talking about fully decentralized application, and we kind of mentioned Akash, Uniswap, and all that, a hosting platform where we can actually start backend and front end. So my question is, it just like when they say God created the world and who created God? So now the blockchain, we say things are stored. So where is the blockchain? Where is the blockchain stored? Like the data for the blockchain, things like that. I don't know if I'm asking the question right, but something like that.
Yes, I think you're right, that when one begins to think about like, what does decentralized really mean? Any question of this kind, like, what is the real meaning of this thing? Whether it's about decentralization
All
or
right.
any other thing in the world, literally, when you dive deep into the meaning, you end up in what is called an infinite recursion, which is this thing that you've mentioned, like, yes, God created the world, but who created God? And we just, so we decentralize our files system, but then like, how do we decentralize the files in that system, and who's like running the file system? And it just on and on and on and on forever, which is why, like, one of the things that I'm reflecting to Mark especially is that it's so much about context, right? That's what grounds meaning in the reality of our lives. It's always context, right? So like, what are you actually trying to do, and what is your intention, right? If you're clear about what you're actually trying to do and your intention for doing it, then that leads you naturally to the kind of decentralization you require in order to truly run whatever it is you're building. How robust does this thing really need to be against censorship resistance, government interference, other kinds of malicious actors, in order for it to achieve its stated purpose and function? So like, I don't think there is such a thing as total, pure, decentralized heaven, right? But I do think that there is a spectrum, and that depending on who we are, what we're building, and why we're building it, we can decide where along that spectrum we need to place ourselves. And that thinking about this is mostly censorship resistance, collusion resistance, and ultimately the intention of what we're building. So,
Beautiful place to end. Thanks, Andy.
Thank you so much, everyone. Gloria, I'll be around in Slack as well. So, yeah.
Bye-bye.
Have a great,
All right, no
great
problem.
week.
Thank you so much.
Bye.